So next we're going to do a couple examples where we put all the pieces together and try to actually sketch a graph. So the example we're going to do first is the goal is to graph the function f of x is 1 over 1 plus x squared. And we're just going to follow through the list we developed. So we're going to first look at 0, which is symmetry. You don't always have to look at symmetry, but sometimes it's useful. And here it will turn out to be useful. So 0, let's look at symmetry first. So to figure out whether it's even, odd, or neither, we plug in minus x. So here that'll be 1 over 1 plus minus x squared. And the negative gets squared away, so we just end up with 1 plus x squared. And if we look at that, if we compare that with up here, we notice that that's just the same as the original function, so f is even. And if you think back to when we talked about it, what an even function looks like, it means if you know what the right-hand side looks like, if you know what this side looks like, then the left-hand side is just the same side but flipped upside, or reflected over. So that means we really only have to concentrate on what the graph looks like to the right of 0, and then the left-hand side will just be a reflected copy, which makes our lives a little bit easier. Okay, and then number 1. Number 1 was intercepts and easy values. So I typically don't spend too much time here unless things are easy to do. So like an easy value might be just what's f of 0. So f of 0 is 1 over 1 plus 0. That's just 1. So f of 0 is 1. That's nice. That gives us a point on the graph. So let's go over here and start graphing, keeping track of all the information. Okay, so what we just learned is that f of 0 is 1, and let's put that here. So we know now 1 point on the graph. Okay, let's go back and continue. So that was the y-intercept. If you think about it, there are no x-intercepts here because, x squared, smallest it could ever be is 0, and so there's no way to get a 0 out of this fraction. Okay, so the next thing, let's look at asymptotes. So the first step with asymptotes is to find them. Are there any vertical asymptotes? Are there any horizontal asymptotes? And are there any slant asymptotes? Well, vertical asymptotes would be when the denominator equals 0. And if you think about that, that's never. There are no solutions to that. So here there are no solutions. For horizontal solutions, remember, the typical way we find that is we ask ourselves, well, what's the limit as x goes to both infinity? And if we're being proper, we should also ask ourselves, because there could be up to 2 horizontal asymptotes, but never more. So we should always ask ourselves, in principle, what's the limit at minus infinity? And if you think about what we talked about before, because the denominator has a larger power of x, these will both go to 0. Okay, so if we put these together, this means y equals 0 is a horizontal asymptote. And it's the only one. And for slant asymptotes, this is also none, since the degree of the denominator is larger. So remember, that can only be a slant asymptote if the degree of the numerator is exactly 1 more than the degree of the denominator. Okay, so now let's go over to our graph and put this information in. So basically, all we've said is that the x-axis is a horizontal asymptote, so I'm not actually going to draw anything in here, but let's remember that. Okay, and then let's move on to number 3. Next, we're going to analyze the first derivative. So this was number 3. So in order to analyze the first derivative, we need the derivative, of course. So the first derivative will be the derivative of, and it's easier if we write the original function as like this to avoid using the quotient rule. So we're going to take the derivative of that. So that'll be minus 1 plus x squared to the minus 2 times 2x by the chain rule. But it's probably easier if we write it in this form to actually think about what it means in terms of the graph. Okay, so this is our first derivative. And when we're analyzing the first derivative, remember we're looking for the local min and local maxes, as well as the places where it's increasing and decreasing. And so to do that, we need to figure out, well, where is the derivative 0 or undefined? There are no places where the derivative is undefined because the bottom's never 0, the denominator. So the only places we have to worry about is when is the derivative 0. And whenever you have a fraction equal to 0, the only way that can happen is if the numerator is 0. So we can immediately jump to just setting the top equal to 0, which means our only critical point is 0 itself. Okay, and so now remember that kind of the easiest way to do this is if you draw a number line, put your critical points on the number line, and then test the value of the derivative on either side. So I'm just going to choose 1 to the right and minus 1 to the left. So if I plug minus 1 into the derivative on the left, so remember this is, we're analyzing the sine of f prime. So to the left, that would be positive 2 over 1 plus 1 squared. So that's a positive number. On the right, this will be minus 2 over 1 plus 1 squared. That's a negative number. And if you think about it, what this means is that the function was increasing here, and then it was decreasing here. So at 0, there was a local max. So let's go put that little bit of information on our graph. So we said 1 was a local max, so that means it goes down on both sides. We don't want to draw it too far because we don't know what happens everywhere yet. But we do know that it will be decreasing to the right of 0 because of the negative and increasing to the left of 0. And we'll come back and use that later after we've analyzed the second derivative. So let's go ahead and analyze the second derivative. And this is number 4. And so to analyze the second derivative, we first have to get the second derivative. So let's do that. So let's just copy the first derivative down here to use it. So the first derivative was minus 2x over 1 plus x squared squared. And we have to take the derivative of this to get the second derivative. And, you know, just to show you a different way, and I think it actually makes it a little easier in this case, is I'm going to think of this as minus 2x times 1 plus x squared to the minus 2. So I'm going to rewrite it like that before I take the derivative, so now I can just use the product rule instead of the quotient rule. Okay, so if we do that, then f double prime, the second derivative, will be, so we have our two pieces here. It'll be the derivative of the first bit, so it'll just be minus 2 times the second part as it is. plus the other way around. So then we have minus 2x times this derivative is minus 2 times 1 plus x squared to the minus 3 now. It goes down by 1. Times the derivative of the inside is 2x. Okay, so if we put that all together, that's minus 2 over 1 plus x squared squared. If we combine all three pieces here, that's a 4, 8 with a positive. That'll be 8x squared over 1 plus x squared cubed. And if we put these over a common denominator, we would, our common denominator will be 1 plus x squared cubed. This will be our common denominator. So what we'll do is we'll take minus 2 and we'll multiply it by 1 more power of 1 plus x squared. And then we combine them. So that'll be minus 2 minus 2x squared plus 8x squared. Okay, and we can combine a couple of these terms. This is the same as minus 2 plus 6x squared over 1 plus x squared cubed. And then we do the same thing we did before. We see where the places where this is 0 or undefined. The denominator is never 0, so we don't have to worry about that. So the only thing we have to worry about is when is this equal to 0. The only way that can happen is if the numerator is 0, so we can jump directly to this. And if we rearrange things a little, we get x squared, or 6x squared equals 2, x squared equals a third. Square rooting both sides tells us that x is either 1 over root 3 or x is 1 over minus square root of 3, right? Because you get plus or minus because you're taking the square root of a square. Okay, so we get two things. Let's put those on our number line. Okay, and we want to test what happens in each region. So the easiest point in the middle is probably just 0. Over here I might choose 1, and to the left I might choose minus 1. Because if you think about it, square root of 3 is bigger than 1, so 1 over square root of 3 is smaller than 1. Okay, so if we plug in 0 to our function, our second derivative, this would be minus 2 over 1 plus 0 cubed. That's a negative number. If we were to plug in 1, we would get negative 2 plus 6 over 1 plus 1 cubed. And you'll see that this is a positive number. Over here you would get minus 2 plus 6 over 1 plus 1 cubed again. And if you think about it, because we knew the function was... Okay, so what we realized here is that root 3, because it changed concavity, right? This is the second derivative, which tells us about concavity. Because it went from plus to minus, this is an inflection point. And this one as well, because it again switched signs, though the other way, it went from minus to plus. And so inflection points will be important. So let's just figure out what the value of the function is there. Let's figure out what's f of minus 1 over root 3. And if you think about it, because we know the function's even, we know that f of the other side will be the same. Okay, so let's go put these points on the graph. Let's say 1 over root 3 is here. And minus 1 over root 3 is here. And let's say 3/4 is about here. So then we'll have a point about here and a point about here, which should be inflection points, points at which it changes concavity. So we might have to change our local max a little bit to fix it. And now let's think about what we learned. We learned that the function was decreasing, or sorry, we learned that the function approaches, so what we learned is that as x goes to infinity, the function will approach 0, and because we know all these numbers are always positive, it'll never go below 0, so it approaches from above. Same as it goes to minus infinity. From the first derivative, we saw that it was increasing to the left, decreasing to the right forever. And in the second derivative, we see that it should be concave down in the middle and then concave up on the outsides. So putting that all into a graph, what we would see is that the function should be concave down in the middle, should be decreasing to the right, and then it should switch to be concave up on the outsides, and it should approach 0 as it goes far away. So it should be something like this. Okay, so this is a rough sketch of what 1 over 1 plus x squared looks like.